Okay, so this is the test review for our Unit 3 and 4 test review. Let's see how this works out. All right, so for our first problem, we've got a hoop rolling down a hill. First thing you need to know about a hoop is that the moment of inertia for a hoop is just mr squared. That'll be accessible to you through OneNote or through the textbook. Any type of moment of inertia for different objects, we'll give those to you. The other thing that you want to know is that V equals R omega, which means that omega is equal to V over R, or the velocity of the radius. Okay, in the beginning of this problem, we have potential energy up at the top of the hill. At the bottom, we have kinetic energy, but it's not just kinetic. We also have kinetic energy in rotation. And so we're going from strictly potential to those two forms of kinetic. Up at the top of the hill, we have the mass of the hoop times gravity times the height at stage 1. All that potential energy is going to convert into kinetic energy, which would be 1/2 mv2 squared plus 1/2 I omega 2 squared. I'm going to do a couple of substitutions. mgh1 equals 1/2 mv2 squared plus 1/2. For my I, I'm going to plug in what the moment of inertia for a hoop is, which is just mr squared. And then omega, instead of writing omega, I'm going to write V over R, and that has to be squared as well. So you can kind of imagine, and this be V2. Kind of imagine those two substitutions. The masses should all cancel. And then this squared is going to go to the V and down to the R. So this r squared and this r squared will cancel. So even though I gave you the mass and the radius of the hoop, you don't need either of them. What we have here is 9.8 times the height, which is 2, equals 1/2 of V2 squared, plus, if I look at all that's left, I have 1/2 V2 squared. If you add a half to a half, you get 1. So this is 19.6 equals V2 squared. And if I square root, V2 comes out to roughly 4.4 meters per second. Oops, I lost my S. All right. So question number 2. We have an object. We have two objects. I always like to draw them and then label them based on what I'm reading. Because the ball is moving 3 meters per second to the right, it's hit from behind. So if I'm thinking about objects moving to the right, I would think of this one here being the 3 meter per second, 3 kilogram object. It's going to get hit from behind by a 5 meter per second, 2 kilogram ball. So there's my initial setup. After they hit, we'll call this object A and object B. Afterwards, we want to know how fast are each of the objects going. Okay? Are they both going to the right? Is one going to the left and one going to the right? What happens in terms of all of that? And so we use our formula. It says the momentum before will equal the momentum after. So the momentum of the first object would be its mass times its velocity plus the mass times the velocity of the second object, keeps messing me up there, equals the mass 2 times VA2 plus the mass 3 times its velocity VB2, which I don't know. Over here, 2 times 5 is 10, 3 times 3 is 9, so 19 equals 2 VA2 plus 3 VB2. That's not finished, but that is a big part of it. I also have the second elastic collision. It's important we understand this is elastic collision problem, which says VA1 minus VB1 equals VB2 minus VA2. The order and the subtraction there is really important. And so we have, in this case, we have 5 minus 3 equals VB2 minus VA2, which tells me that VB2 is 2 plus VA2. You can imagine kicking that guy over, he'd add over. This is the substitution that I'm going to do right here. So we're going to bleed down on the next question, but we have 19 equals 2 VA2 plus 3 times 2 plus VA2, little distribution. This right here is going to be a 6, which I'm going to minus from both sides, making it 13 equals, and then this is 2 VA2, this would be 3 VA2, that's 5 VA2, we divide by 5, VA2 is 2.6 meters per second. Because it's positive, we assume it'll go to the right. For VB2, we look at taking 2.6 and plugging it in there. VB2 is 2 plus the VA2, which would make it 4.6 meters per second. Again, because it's positive, we'll assume it's to the right as well. Okay, I'm going to have to clear a bunch of that to make room. Okay, I'm going to have to get rid of those. Okay, so the next question has to do with a box being slid side to side or being lifted up and down, and then asking how much work is done, and then if we did it in a certain amount of time, how much power does that take? First thing you have to understand is that when you slide something at a constant velocity, there has to be a balance of forces. And since I'm applying a force to the right, there must be a force to the left. We're told that there's friction involved. And so the force of friction and my applied force have to be equal. The reason that matters is because work, we know, is defined often as FD cosine of theta. Why do you know how much force I'm applying? Well, my force depends on frictional force. We're kind of intertwined. And the force of friction is equal to mu times the normal force, which in a horizontal sliding across the floor kind of problem has to equal the weight of the box, or its mass times gravity, which would make this mu mg. This would be my applied force. So when I talk about how much work is done, I take my mu mg times the distance I move it of 3.2 meters times the cosine of theta. Now, if I'm pushing to the right and it moves to the right, the angle between those is 0, and the cosine of 0 is 1. So all I have left to do is put in my numbers. Mu for friction in this was 0.25. The mass of the box was 80. Gravity, of course, is 9.8, and I'm doing it for a distance of 3.2 meters. In this problem, the work comes out to be 627 joules, roughly speaking. At the end of the problem, you're asked to find the power. Well, power is defined as work over time. So we would just take that work, 627, divided by the 2.3 seconds, and we get roughly 273 watts. That depends on whether you're rounding along the way, but you should have something very close to that. Okay, for the second part, okay, let's erase a little bit of this. We don't need all that information. Okay, this time we're just going to lift the box instead of dragging it across the ground, which you might think, oh, we don't have to deal with friction, that's awesome. It's actually harder to lift things than it is to push them across the floor, because while friction isn't our friend, friction's a little bit nicer than gravity is. And so as we go through this, in this case, if I'm going to lift a box, I have to have an applied force that's going to equate to gravity or to the weight of the object. And so that's 80 times 9.8. If I know how much force I'm applying upward, and I know what distance it's going to travel, distance of 3.2 meters, I'm ready to go. The work done is the force times distance. Well, the force in this problem is just mg, so 80 times 9.8 times my distance of 3.2 tells me that the work I'd have to do would be roughly 2,510 joules. And if I wanted to do that in a specific time of 2.3 seconds, you just divide that by 2.3, and the power rating required would be around 1,090 watts, depending again on how you round along the way. Okay, let's look at these last couple of questions. The skateboarding question, just so we're clear, there's a skateboard sliding to the right. It has a mass of 2 kilograms and a velocity of 5 meters per second. As it goes along, Mr. Welch is going to step onto that skateboard, assuming that I had no initial velocity, meaning I'm not helping this thing go along. I literally just stepped onto it. Because the mass has now increased, it's going to have to slow down for momentum to be conserved. This would be an example of an inelastic collision. And so you'd have the momentum of the two individuals before, 2 kilograms times 5 plus 65 kilograms times my 0 would equal our combined mass of 67 times our new combined speed. Well, 65 times 0 is 0, so I'd have 10 divided by 67 equals V2, which makes V2 roughly 0.15 meters per second. Slowed it down significantly. It's barely moving at this point. All right, last question is our Fulcrum problem. I'm going to try to do this the most appropriate way. Keep in mind, 5 kilograms is not a force. 3 kilograms is not a force. Really, to find the force, you would need to take the mass times gravity, because that's what's going to be applying a downward force. And so for each of these, when I do force times distance or force times location, okay, I have to recognize that, again, it's not just 5, it's 5 times 9.8. That is consistent across the problem, but the first thing that we want to do is figure out which one is bigger. And so over here, if we found the torque, because the torque here and the torque here, they really need to equal out, or else it's going to start to rotate and spin on us. We don't want that to happen. We want it to stay stable and balanced. And so if we talk about the torque, torque is FR sine of theta. Now we're going to assume that this is at a 90-degree angle due to gravity, so I don't really need the sine of theta. But the torque of the 5 kilogram mass would be the mass 5 times 9.8 times the radius, and it's at 0.72 meters. So the torque of the 5 kilogram mass is roughly 35.28. Okay, over here when I do the torque on the torque of the 3 kilogram, it's again 3 times 9.8 times a radius of 0.8 meters, and so the torque of the 3 kilogram mass is 23.52. Now before I go any further, I want to acknowledge that because this is the small side, now I don't know that until I've checked, but that 23.52 is too small. So this 2 kilogram guy, he belongs over here. That's important because I want the two torques to be equal So over here I'm going to add the torque of my 2 kilogram, which would be 2 times 9.8 times an unknown radius. I don't know that radius, but I do know that if I were to subtract 23.52 from both sides, I'm going to get something like 11.76 equals, and this guy right here would be 19.6 R. If I divide by my 19.6, the radius I need to put it at is at 0.6 meters. Now I need to point out that that's, again, on the right side of the fulcrum. Okay, so that's important. Let's say 0.6 meters to the right of the fulcrum. Okay, so that's answer number 1. There is a follow-up, because with all of these forces pushing down, something has to push back up, or Newton's law says it accelerates downward. So there must be an upward force. And that's what we're looking for in the second piece. Well, if we just consider the 3 downward forces as just being down, and the center force as being up, we know that those 3 forces down have to equal the 1 force up. So the force of the fulcrum has to equal the force of the 5 kilogram plus the force of the 3 kilogram plus the force of the 2 kilogram masses. Now the good news is, because they're all pointed in the same direction, I can just combine all of them and say that they have one big mass. 5, 3 plus 2 is 10 times gravity of 9.8 to get a 98 Newton force. If the fulcrum can't supply that force, it'll be crushed by all of the mass that's on top of it. All right, that's it. I hope that's enough to help you get through it. Good luck.